Alright, so in this tutorial, we're going to go quickly through some of the key features in HiPhyEngine and set up a very simple simulation with Affine body with it. If you have HiPhyEngine already installed, if you go to the fixes panel, you should see the HiPhy right here. Turn on the screencast. Alright, and to make it Affine body, you just turn it on and choose the material type Affine body. Affine bodies are very similar to rigid body. They do have a stiffness here. However, if you don't, for all intentional purposes, from artist's perspective, they should be treated as rigid body. The stiffness here, you just intend to be as stiff as possible, so that there should be no visible deformations that you can see during animation. Now we're going to make it collide with something, so we're going to add a plane and then scale it up and then move it down. Now there it goes. And then we're going to make the plane a collider right here. And you'll notice that first parameters in both of them are what they call a solver node. So because HiPhyEngine have to be with interacting with only the Blender Python API, but not the C++ API, we do not have a lot of access to a lot of the functionalities API calls that the internal solver have. Therefore, we have to play around with it a little bit. How we do it is everything is connected to a solver object, and when the simulator runs, the solver object will go through the whole timeline, export all the animation relevant data to an external stage, and will run simulation on that stage. And when it finishes, it's going to bring the result back. And to create a solver object can basically be anything you wanted. To make things simple, we're just going to have empty plane access here, and we're going to rename it solver. And we're going to choose Lagrangian solver. Lagrangians are for cloth, rigid body, and hair and all the stuff, while NPM is for NPM meshing particle. In this case, it's going to be a Lagrangian. We're going to choose the solver as the object for both. All right, there it goes. And if we run the simulation, and both of them need to be triangulate mesh. Almost all simulators requires object to be triangulated, so we're just going to add the two objects are triangulate modifier. So almost all simulators use triangle collision detection. However, a lot of them, what they do is that if they accept quad mesh and other type of polygons, they're going to triangulate them internally. They might sound convenient, but it will cause a lot of issues because when your input mesh does not match your simulation mesh, a lot of times you'll run into like the collision is fine with the triangular mesh, however it fails. It looks like it fails with the rendering mesh. In this case, for HiPhyEngine, we want user to explicitly doing triangulation themselves. They might have the preferred direction. For instance, if you think this as a rasterized grid, you may want to all the triangles to have the same direction, then it will favors one bend direction. You want some type of alternating triangulation. And then if your rendering mesh looks poked through, you can see the simulation triangle mesh and say, oh, it's actually clean. Because what we can guarantee in HiPhyEngine is only that the triangulate mesh that's used for collision is intersection free. But if you're adding other types like subdifferent surfaces or other things, it can still end up going poked through. Later in the series, we'll going through how to fix that. But it gives user a way to debug to see, okay, the simulation itself is clean. It is the visualization and all the rendering stuff that's causing things to go through. Then I need to potentially increase the collision radius, increasing the collision stiffness, so that things has more tolerance to push doing simulation. All right, and another thing is notice is that the gravity in HiPhy is y up, Because HiPhy is designed, we want to comply to the industry standard instead of the Blender standard. Blender is ZApp, and gravity is the only parameters in the in HiPhyEngine that has any sense of direction. So just this is the only thing you need to change. So change from 0 to negative 980. All right, and then if you run the simulation, there it goes. It falls and collides with it. We're going to add another. Let's go back to time. Sure. All right. We're going to just add another affine body as well. Just to make things a little more interesting. So we do the same. Add the cube, go up and go to the left. Side rotate it. All right. That's good enough. HiPhy, affine body, solver. Set the gravity and triangulate. Right. So round sim, and there it goes. Before we end the first tutorial, we're going to go through something very important called solver scale. I know because a lot of people their Blender thing is going to be in meters, instead of centimeters. So this is something everyone going to touch first and run into issue with. Notice that gravity here is 980, not 9.8, because HiPhyEngine's internal unit is centimeter. What we allow user to do is that there is something called solver scale. The idea of solver scale is it scales the whole scene by the solver scale internally. So if the whole scene is in meters and inside the solver is centimeter, when they go inside the solver, everything needs to be scaled up by a factor of 100. So when the solver exports the whole scene, you're going to scale everything up by a factor of 100 to match the internal unit. And then if we run the simulation, it looks a lot heavier. See? And now you notice why it's called affine body. Because objects right now are not stiff enough anymore for this size, what happens is it stretches and shears. And the only thing allowed on A are affine deformations. So we can just increase in stiffness to make sure they're stiff enough. And then run the simulation again. And they're a little bit better, probably needs more even stiffer. Another thing you can do is reduce the density. In this case, affine body doesn't have a mass. The reason is to compute the center of mass, you need to do a surface integration, and we do allow user to paint the density on the surface. So for instance, if you have a hammer, you have one side very heavy, one side very light. Instead of just letting user to specify what the mass of the object is and taking the geometric average, you could paint a map that's the hammer side is very heavy and this side pretty light. So then the center mass will be computed properly. So now if we run this simulation again, there it goes. Now it's all fine. So that's it. Actually, before we go, I'm going to talk about another thing that's related to the solver scale. As I said, the solver scale converts the scene unit into the solver unit. So in this case, the scene unit is meter and solver unit is centimeter. So we get 100. And all the parameters that's in the proper unit will be automatically converted because they're in the right unit. Besides, there are certain parameters called called model units. The idea of model units is that those units I want the user to have a sense of how large they are given the scene. So ideally, like for instance, the thickness here are in model units. The reason is that when things are colliding, I want user to know like how thick they are when they considering collision. In this case, it will be 0.1, and that is not 0.1 centimeter, that is 0.1 of the scene unit. So because the cube is 1 by 1, so essentially going to be 1/10 of the cube size. And this does not scale with the solver. So before, when we're in centimeters, it will be 0.1 centimeter. Now we're in meters, this is 0.1 meters. I know that a lot of people run an issue is that they change their solver scale. However, they also need to change the thickness of the object. If you're in centimeters a lot of time, if you cloth, this is going to be 1 decimeter, that is very thick cloth, and you need to significantly reduce that to match what the parameters, whatever parameter you want to be. So that can be a catch for a lot of people. And that's it. That's our first tutorial, and you learned how to set up a simple simulation and some of the key features in Affine body. And see you next one.